welcome everyone. I've learned most of your names already so far, but we'll get into that soon. Welcome to RAP. Vaibhav and I, we were in the project last year during its pilot year, and we had a lot of fun, learned a lot. So we've been working hard this summer to kind of transition it to an in-person format, added in a physical, hands-on side of it, and we're really excited to be teaching it. So hope you guys enjoy it as well. Just a quick couple logistical notes before we kind of get into it. You all should have received an email around 7 a.m. this morning.
Did anyone not receive that email? All right, fantastic.
Whatever, James. Okay, so just a couple reminders. There's a when to meet form in there. Please fill that out as soon as possible so we can kind of know when to, we're going to use the responses to that to plan which day and time of the week to hold future lectures for fall quarter. There's some, we request a deposit for this project. I added some instructions to that. You can be either cash or Venmo, and I added the Venmo information to the syllabus very recently, so go ahead and check there. So just get that in by project for lecture 2. There's a shared drive. We'll be posting all RAP materials, so lecture slides, recordings, assignment specs, etc. in there, so just make sure you're able to access that. And lastly, there on the IEEE Discord, you should join the RAP channel so we can communicate more quickly, casually through there.
Yeah.
So you have to go to the add roles channel and react with the cell phone thing. I don't know. So do that to keep in touch. So with that said, I think some introductions are in order. My name's Tyler. If we haven't met, I'm a third-year electrical engineering major. I'm a very big Weezer fan. If you haven't heard of them, here's a picture of me a little over a month ago at a Weezer Green Day Fall Out Boy concert in San Diego. Cool. Vaibhav's been trying really hard to get me to wear a Hawaiian shirt to lectures. It hasn't worked yet, but we'll see if my resolve is maintained. Then another fun fact, I've done Brazilian Jiu-Jitsu, Judo, and wrestling for the past 12 years, so feel free to talk to me about that later. Cool. Vaibhav, go ahead.
All right, I'm a 4th year EE major. Tyler's BSing. I will have him in a Hawaiian shirt by week 2, and if not, I'll try and always be in one. So you'll have me to lighten up your day and distract you from rap lectures that can sometimes be a bit heavy. I enjoy reading, biking, and comedy. I listen to some rap music. One thing that I suppose I'd like to get out of the way, and I genuinely mean this as a open thing, I do tend to swear a bit. We're all college students. I'm not going to particularly bother censoring myself during lectures. If that bothers anyone, let me know. You don't have to let me know right now. You can anonymously email us, Discord message me, whatever. If you let me know, I'll stop it. So let me know about that.
There you go. So that's us introducing ourselves to you guys. Now we want you guys to get to, it was very deliberate that we haven't formed teams yet because we want to give you guys a chance to know the other people in the project, and then we'll form teams shortly thereafter, sometime in the next couple weeks.
In terms of timelines, we're looking at teams probably by assignment 3-ish, maybe halfway through between assignment 2 and 3, because that's when you start really putting a design for the module as a whole together. Before then, I really encourage you to talk to people in the project, figure out, what part of the project you're most interested in, what part of the project they're most interested in, try and get, people together in groups with slightly diverging interests so that the team as a whole is engaged throughout the project, stuff like that. We didn't want to assign people blindly as all.
So with that said, a very a silly icebreaker. So in groups of about 3 to 4 people, just group up, share typical name, major, year, and then we have a very important question for you. This one of our mutual friends wrote this thing. So you have to decide if you think I should wrap it or Vaibhav should wrap it. live immediately after, and just give a quick justification. Your justification can be, I hate Bob, so like whatever. Just a couple minutes.
Or your justification can be Tyler isn't in a Hawaiian shirt. How dare he disappoint you like that?
It's a little Hawaiian. It's like 60% Hawaiian shirt.
I promised you 60%.
Yeah. All right, so let's take 2 minutes, and then please vote for Vibog and get.
Hey, no biasing the polls. Also, the person who wrote this is Aircopter lead Alexi. You'll interact with him a fair bit if you're in the lab over the year. I can only recommend a 10-foot distance. But yeah.
Alright, well, you guys figure it out. I don't know. Be social. It wasn't that funny, but
Yes, it
Dude, then all the doors to anything for a loss.
Grab a seat, make sure you can see this whiteboard, and we're doing an icebreaker right now.
You're doing
My
an
name is
icebreaker.
Monty. I'm also a second-year transfer meeting major.
Pavel, Noah. Yeah. Yeah, you guys know.
Did you transfer or did you start?
Yeah, I started.
Okay. This is your last year? How does it feel? You want to be done with this? Dude, I already feel like I want to go work. It's hard enough. Transfer?
No.
Okay. Well, I guess we just. Wait, so, are you all going to specialize in like circuits and electronics?
Extend my skill set. And you're assuming you already have taken all the like prereq classes. I've only taken one or two prerequisites for this.
Yeah.
I mean, like, you can understand. I enjoyed it.
It's really fun. But it's also
Yeah.
Who did you take it with?
John. He's like a young dude.
So like, do they actually come and
Yeah.
check it out and all that?
I don't.
Okay. Alright.
You what?
I took it with like.
I was on my way up.
Okay.
I was in the left, and it was right next to the center.
Oh, wait, engineering 4 is blocked. So
No, that was me, but yeah, I was on it. And I saw you were
Yeah.
But yes, all the other, like the side entrances and the main entrance is blocked.
And then you take 113.
So I went into Bolter, got up to the 7th floor, and then walked across. Yeah.
Wasn't he good?
Yes.
I don't for one for
Okay. What's your name? Carmen. Oh, yes, yes.
Hey, Alex, grab a seat. We're doing an icebreaker.
Come join here. Okay. Introduce yourselves again for who?
Yeah.
I'm Nathan.
I'm Ramtin.
Noah.
I'm Connor. Connor. Nice to meet you. What year? What year? Oh, junior. Junior. Very cool. Very cool. I can start. 131.
131 you said?
Oh,
Yeah.
So, we should have someone. I think there's like Diode or.
Okay.
Yeah, no, the one.
Yeah, I was
This is again,
Yeah, this is-
115A, 170A.
Yeah, that's true.
CS35L. And 112.
CS35L?
Yeah.
Why are you doing 35L?
Oh, I'm doing like I'm doing the CS Tech
101A.
and then I want to do like software stuff, but I have to teach that class.
Okay.
Oh,
and
gotcha.
113A and
Pretty boring.
although I'm just not taking
131A and 113.
8 and 11 and then 131.
I took it last year. It is so hard.
Yeah, you take it right in the right place.
It was like a
Well,
business. He's like old. German.
Kenny.
Yeah, probably.
Yeah.
It's like living or something.
Oh yeah, living back in
Yeah, we're.
Oh no, that's my advisor.
So he's German.
Which one are you?
I thought he. Okay.
Alright, guys, let's bring it back.
Yeah, sure. It'll make more sense.
Alrighty.
So,
Let's see. How do you want to
so
do this?
show of hands, people who think Tyler should do this. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, and people who think I should do this. 1, 2, Tyler,
What?
you're up!
Oh, man.
Come on,
Alright.
music fans.
Are we gonna acapella?
You need
this?
to move to the right of the podium.
I need to see the lyrics though, bro. Alright.
No, right of the podium, Tyler. Right? You need to be in the recording.
That's what I'm trying to avoid. Okay. Hopefully this doesn't. This is more fun than cringe, but it might be more cringe than fun. We'll find out. Yeah. You're working on the wireless advanced project. Bring a Smith chart and a compass for this wireless advanced project. Yeah. Give me everything you got for this wireless
Advanced
project. Lecture's long, next required. Put this function right in the Laplace. Splice the circuit like an Indian bazaar. It's an attached, don't put it aside. I do a vector analysis while it's inside. Turn on your circuit, look in my eyes. This project is wireless. Come take a dive. Try it out. You'll be surprised. Oh. Thank you. Oh, okay. I don't know why we decided that was a good idea, but it happened. So now it's there for all posterity. Okay. That said, okay. Thank you guys for bearing with that. Hope you guys got to stop laughing. All right.
I love it.
Alright, with that, let's get down to business. Lecture 1.
All right, Bob.
Sorry, for those of you who came in real late, we covered some logistics stuff. It's on the slides of it's in the slides. They'll be up later. You can catch up through the recording as well.
Yeah.
All right, let's go.
So here's kind of some of what you should expect to get out of this project throughout the year. I'd say the overarching umbrella thing over everything is you will learn kind of the system architecture of how do you build what goes into a wireless digital communication system. So on the hardware side of things, you'll be designing and implementing a lot of the common RF circuit components, things like amplifiers, oscillators, mixers, filters, the whole 9 yards. Then you'll be actually assembling this stuff and working with the physical components. So you'll be winding your own transformers, you'll be designing a PCB, ordering it, assembling it, testing it, all that. On the software end, we'll be doing, we'll be implementing some common DSP signal processing algorithms on a STM32 microcontroller. So FR filtering, a lot of other things that go into that. We'll be simulating the communications system, the hardware using LT-Spice. If you don't know, it's a free open source circuit SPICE simulator. In MATLAB, you've probably used it in one of your classes by now. Let's see. Then to top it off, once you actually assemble this thing, you'll find out, like Bob and I found out that it won't work first try or the 10th time. So you'll be getting very familiar with oscilloscope, signal generators, vector network analyzers, and the like. Let's see. So that's kind of what you should expect to get out of the project. So what is the project? Well, it's going to be two microcontrollers. You have a transmitter and receiver. We're going to talk to each other. Vaibhav, do you want to?
Sure. So on the transmitter end, we're gonna have a microcontroller that generates a set of bits and maps it using a modulation scheme called BPSK, maps it to symbols that we then transmit. If you've taken 113, you might already be familiar with some of that. If not, we'll go over what that means later towards winter quarter. Once we have that, we'll be outputting from our microcontrollers. Now, microcontrollers, especially the ones that we use, output signals at 1 megahertz. Leaving aside some of the difficulties of trying to get a transmitter that would transmit a signal like that, there's also some regulations that you have to keep in mind about what frequencies we can transmit it as hobby radio people. The lowest one and the easiest one to work with is 27 megahertz. So what our hardware modules, the receiver and transmitter boards we'll be building, what those will do is take the 1 megahertz signal, convert it to 27 megahertz, and then put that into the antenna. What the receiver module does is basically take that same thing, amplify it a bit because it's lost a lot through attenuation in the air. Again, down convert that back to 1 megahertz and input that into the microcontroller on the receiving end, where we again do some digital signal processing to convert the sine wave, modulated sine wave that you get back into ones and zeros.
There we go. So just how is that gonna fit into the year time-wise? In the fall, we're going to be focusing on a lot of the analog hardware circuit design side of things. So we'll be doing a lot of SPICE simulation, again, multi-SPICE are some of our modules. In winter, you'll be in teams by then. You'll work together to design physical PCBs for a transmitter and receiver. While those are on the way, we'll start to dive into some of the DSP concepts. Then in spring, assemble the system, and then take your MATLAB communication system simulation, translate into C, stick it on a microcontroller, and then put it together. And hopefully by the end of the year, we hope all of you will be on a team with a working communication system to show for it. So
Also, real quick, we're not going to do the whole hey, any questions so far thing. If you have a question, just start talking and we'll stop.
So welcome.
Welcome to Rap.
Okay. Let's see. Yeah. So we're gonna switch over to like 2 minutes. We're gonna switch over to the technical portion of the lecture. And that was just kind of the intro part, overview of what we'll be doing. So we reconvene in 2 minutes.
Wait, what do we need to reconvene? Can we just go?
I don't know if they want to go. They can go right now.
Sure.
Oh, I think this is.
Oh, Jesus Christ. When did that happen?
I think it just happened actually. I saw it rotate.
Oh, crap. The shit.
You got it, man.
It's quite the video quality.
Hopefully we can cut this out.
Somebody just hold it.
I mean, technically,
Isn't there like a thing to tighten it?
There we go. All right.
you just need
The gimbal just switched off for a second. All right, we're good.
the recording still
Yeah,
still
the
on.
recording is still on, along with that slight segue.
Okay. Sure. We can just
What are you talking about?
yeah, we can just get started and get you guys out of here hopefully before 8. Yes. So yeah. So today we're going to be talking about amplifiers. Go ahead. Next slide. So amplifiers are a very important element of an RF system. Most obvious example, the first one comes to mind is, oh, I need to transmit an antenna. I need to boost my signal up to give a lot of power to transmit over enough of a distance, and then it gets picked up by an antenna. It's going to be attenuated really small through the air. You need to fly it back up. And there's some other applications we'll see as well. So we're going to be using bipolar junction transistors in the construction of our amplifier circuits. So before anything else, we're going to do a really quick.
Yes.
You figured it out, right? So we'll be doing a really quick review of some of the basics of their operation. Once we go through that, we'll cover 2 really common amplifier circuit topologies, namely the common emitter and common collector. More on that shortly. So before anything else, so what's a transistor? So transistor is a 3-terminal device, and they're so I'd say the best way to describe their usefulness is that basically you can control a large current from between 2 of the terminals using a really much smaller current through the 3rd terminal. So in route we're going to be using Npn transistors. They're named as such because they consist of a p-type semiconductor sandwiched between 2 n-types. And let's see, yeah, so for an NPN you have a collector, base, and emitter.
Yeah, one thing to make clear here is we're not going to go too much into the semiconductor physics of this stuff, nor too much into all the theory of the multiple ways you can use them. We're going to give you like a 20-minute run through of how they work, specifically for the application we want them for, and kind of leave it at that and move on and like basically treat it as a block with certain equations it has. If you are interested in learning more about all the theory for this, I recommend ECE 115A, or you can come talk to us after lecture and we can point you towards some fantastic online resources.
Yeah, so said, how do we use these things? So the usefulness of BJT comes from their IV characteristics. So the first thing when you're trying to use it is you need to turn it on. So so there's normally there's a current flowing through the collector, through the emitter, but in order for that to flow, you need to forward bias the PN junction between the base and the emitter, and that happens when you apply a voltage greater than about 0.6 to the base emitter terminals. So let's see. So once you have it turned on, so it's conducting now, then there's kind of 2 operating regions that it could be in. If the voltage between the collector and emitter is less than 0.2, you say that this device is in saturation. You would see this kind of more in switching applications, but we won't say much more about that. The region we're interested in is called the forward active region. So once it's turned on, you have a sufficient voltage across 2 terminals to forward bias your transistor. Then turn on, and then there will be an exponential relationship between the current flowing through it and the voltage you apply to the base terminal. So this is kind of a freaky graph, lots of numbers. Let's just focus on this part over here. So each of these lines is 20 millivolts apart. So this is 750, 770, 790. Okay. So you notice when the voltage increases 20 millivolts first, there's about a 0.25 milliamp increase. Another 20 millivolts. Now it's half a milliamp increase, and it's a full milliamp increase for the next 20 millivolts. So it's an exponential relationship. Go ahead to the next slide. So just to show that a little more explicitly, so the current flowing through the device and as a function of the voltage you apply to that terminal is kind of summarized by this equation here. If you take in 115A, this is pretty much the ideal diode equation. So you can see really clearly that at about after 0.6, it starts, you see this exponential curve. This equation here, IS, it's the reverse saturation current. That's just going to be an intrinsic property of the transistor you're using. You can find that on data sheets. VBE, that's just the kind of our input. And VT, if you haven't seen that before, that's called the thermal voltage. If you don't know anything else about it, just know that at room temperature, that's going to be 26 millivolts. Remember that number. Okay, 5 above. Yeah. Okay, so now that we've kind of mentioned those things, let's talk about amplifiers. So to put it simply, what an amplifier does is it takes something small and it makes it bigger by some factor. So here, for example, we have, let's say we have a 1 millivolt peak to peak, so it's centered at 0. We have a sine wave going from 1 millivolt minus 1 millivolt. Great, and then we put that into the amplifier, then on the output, maybe it has a gain of 10. It's going from 10 millivolts to minus 10 millivolts. So,
What we're exploiting here is this exponential nature, because fundamentally what we're saying is a small change in VBE is a much larger change in IC. So these amplifiers are exploiting exactly that exponential nature, which we will.
Wait, go back. Yeah.
Yes.
When it's a sine wave, you kind of distort it because it's not linear.
Yeah, so this kind of gets into what we call small signal. So the actual amplitude of our input waveform is going to be relatively insignificant to the DC voltage you apply at the sink. So we said we have I was gonna get into biasing.
So we'll get into this in just a second, but that's called, so that what you're touching on is the idea of biasing. What you do with a transistor is you use larger DC voltages to set what point of this exponential curve you want to be at, and then you overlay a small AC signal on top of that DC signal that's actually getting amplified. And for the AC signal then, once you're at the set point of the exponential, you can treat that small section of it as linear.
Go back to slide.
Does that make sense?
Okay. So here's how I explain DC biasing. So if we take our signal, it's 1 millivolt peak to peak, and I just stick that right here. What's going to happen? There's a 1 millivolt minus 1 millivolt on the base emitter there. Actually, if that's all you've done, then nothing's actually going to happen, because the transistor is going to be in cutoff, because it needs to have. Remember from the previous slide, that voltage needs to. It won't even start conducting any current until it gets above some threshold turn-on voltage. So the trick to get around that is you superimpose your alternating signal onto some DC offset. So instead of oscillating between plus 1 millivolt, minus 1 millivolt, you like add 0.7 to it. Now it's going to oscillate between 0.701 millivolts and 0.699 millivolts. So now the transistor is in the right operating region, and it's still seeing that superimposed signal on it. So go back to this one. Yeah. So that said, 1 millivolt is much smaller than 700 millivolts, right? So, yes. Yeah, see, all right. So if you zoom in really close here, kind of what you'll see is the exponential appears approximately linear at that voltage scale. So when we have when our input and output is relatively small compared to the DC biases and those terms, then we can approximate this as linear, right?
Something you'll start seeing though when you start cascading amplifiers, for example, is exactly some of that non-linearity creeping in. And so there you then have to start balancing, like try to split the amplification so that what you get at the middle stage isn't too large, so that you're amplifying by equal amounts at both stages, or even purposefully not amplifying by too much at the first stage. So that's something that you'll have to start considering when you get into the designs a fair bit later, when you start cascading these.
Okay. So like we just said, so when your signal has a relatively small amplitude compared to the DC bias, then you can linearize the behavior of the transistor, and there's two equivalent models here. These are used in derivations, but we'll just kind of show you the end result of the formula, so don't worry too much about this. You can refer back to these later when you're doing the assignments if you want to kind of learn. This is more here for reference, but don't write everything down. Okay. So that said, let's build an amplifier. Yeah. Okay. So we have some signal, and we have some voltage signal. Let's stick with the 1 millivolt minus 1 millivolt thing. And we want to amplify that and turn that into a voltage. If we go back 2 slides, or one more slide. So if we stay here, then I can change VBE all I want, but this node is gonna it's tied to ground, it's gonna be 0. The one up there, it's gonna be tied to 5 volts, so you're not gonna get any, there's nowhere to pull out and output voltage. The current will be changing, but you can't really use that as easily. So the solution to that is we just stick a resistor at the collector terminal. Now, when so we changed VBE, we're changing the collector current, and then that collector current is going to flow through that resistor up there, and Ohm's law, there will be a voltage drop. So if there's 1 milliamp collector current, then the voltage at Vout will be 5 minus 1 kiloohm times 1 milliamp equals 4 volts at the output. So that's what we mean when we say the collector resistor converts the collector current into a tangible voltage drop we can work with. So you'll notice that the higher VBE goes, the more current flows through, and the larger that voltage drop. So as VBE goes up, Vout goes down because it's being subtracted. So that's what we say that the amplifier is inverting. So it's just multiplied by -1.
Quick question here. So if I go back a few slides and I come to operating region, it said that for a low VCE, I fall into saturation where the transistor is used for switching. If we want to be able to use it for amplification and to stay in this neat exponential, we have to ensure that VCE stays larger than about 0.2 volts, which is the saturation cutoff. Now, the issue here, if you may have noticed, is E is 0. If I make this resistor too large, or if the current through here gets too large, then Vout becomes so small that this voltage goes below 0.2. And the moment that happens, I fall into saturation. So that's something you want to be somewhat careful of, and we'll get to that later, about how you can work around this maybe even, and other things like that. But you want to keep in mind that at the end of the day, you don't want to mess with your DC bias, and you don't want to exit forward active region. So this is something you call headroom, and the idea is that RC eats away RC eats away at your headroom. So you have a headroom of 4.8 volts because 5 minus 0.2, and the larger the RC, the more you eat away at that headroom.
Okay. So if our entire amplifier was just this, then this would be kind of the input-output characteristic curve. So let's see, the red line is just the collector current, and then the blue line is the resulting voltage drops across the thing. So so remember earlier we said we could, if our signal is relatively small compared to everything else, we can treat it as we can treat the exponential curve as approximately linear. So in other words, the gain you'll see is going to be the slope at the bias point. So like if you go back 2 slides, like here the slope is relatively low, so your gain is going to be smaller than if it were really steep. Then a smaller change, small change here would lead to a larger increase there. So you can kind of see that. So to actually go back. So to actually calculate this, I can do a derivation later if you're so curious. But basically, you take that you take 5 minus RC times that exponential thing. The math works out. You'll get this. That the gain is equal to minus GM times RC.
GM is the transconductance of an amplifier. The definition for it is up here. IC here is your DC biasing IC. So you start by DC biasing your transistor to be in forward active. Once you have the numbers you're working with based on the specifications you need to meet, you then start choosing your RC and then iteratively manage the trade-off that comes between a larger IC and RC, how much headroom you have, stuff like that. We're going to be talking about the steps you need to take throughout this lecture. Assignment 1 will also kind of walk you through exactly that process.
Okay, so how are we feeling so far about
Yeah.
what we've done? Good? Okay? Meh? Alright, that's good.
Alright, so let's start biasing, or let's start circuit designing by biasing. So if, Tyler, can you see how this lines up?
Hey Nathan, do the thing.
So the idea for biasing is, I don't need to be in it, it's more the whiteboard.
Okay.
Yeah. The idea for biasing is that we want to set the quiescent operating point. That basically just means the point that the transistor operates at if the input I'm giving it, that is my small AC signal input, is 0. Basically, how does the transistor behave at DC voltages? AKA the state where there is no input. So a good bias circuit is one that's independent of temperature, because the transistor is, at the end of the day, it's Npn, it's layers of semiconductor. Electrons and holes get more excitable when the temperature is higher. All that fancy stuff happens. We don't really trust the transistor too much. We want to give it a very small job in setting our bias point. And secondly, we don't want it to depend too strongly on supply voltages. Quick mental exercise here. Let's say I want IC. So this was my equation for IC, some exponential, right? So IS is going to be some small value, usually it's some tens of nano or picoamps, right? Let's just say it's 10 picoamps, random number. So let's say I want to set an IC of exactly 1.2 milliamps. That means I need to now go on DigiKey and find a supply voltage. I'm not doing the math here, these are numbers I'm randomly pulling, but I need to find a supply voltage for VBE that is exactly equal to 0.53864 amps, 4 volts. And if it deviates from this even to 0.5486, this goes from 1.2 to 1.4 because it's exponential. Good luck finding that anywhere. You're not going to. And even if you do, it'll naturally drift just as it discharges. So we want to be able to find a way to be independent of supply voltages, or set it in a way that we're only relying on one supply voltage that's of a standard value. And second, we want to be independent of temperature. Tyler, if you can go back a quick second to the small signal model. Beta is highly temperature dependent. So the two intrinsic properties of the transistor you'll be working with most closely are beta and GM. Beta for transistors is basically defined as their current gain, which is in forward active, how much do they amplify the current. For the transistors we'll be using, you can mentally say beta is about 100. And just run with that number. GM obviously varies with IC, but beta varies a lot with temperature. On most data sheets you'll have a range from like 60 to 400.
Yeah, it's a pretty large
Pretty
range.
big range. Yeah, so if you want to go back. Alright, so let's start by getting rid of the voltage dependence. So if I give you 5 volts and simple circuit components, resistors, capacitors, inductors, how do you get this voltage?
A resistor. You want off it to have a voltage drop to that?
Okay, but a resistor between what and what? A single resistor?
I would just get a potentiometer and turn it on until I get that.
That's fair. What is a potentiometer at heart?
What is a
It's
potential?
just 2 resistors.
Exactly. A resistor, resistance divider. Resistor
A bit-
divider?
a bit-
Voltage divider. There we go. Voltage divider. That's the word I was looking for. Sorry. Yeah. So voltage divider. So if you turn your eyes there, that's the second stage. So we go from this as our VBE. We go to this, where VCC is now a standard value like 5 volts, 3.3 volts, whatever you'd like, something in that ballpark. And this is now a voltage divider, where I have a lot more control over setting the voltage at this point, because R1 and R2 are generally a lot easier to find a whole diverse range of values for. Plus there's the fact that with R1 and R2, because it's set as a ratio of the two, even if I can't find the exact specific value for one, I can usually do some fancy tricks with series, parallel combinations of different resistances if I really have to, and get just about any bias point you could possibly want. Alright, now we can do the math here, but I don't really think we need to. So if you look at the current equations over there, here we already know that IC is this, right? Here, IC, if you solve, you know, standard KVL stuff just by doing that, it's this, which is simply the voltage divider for VCC, minus VBE, which is the voltage from here to here, divided by this. And where I got R1 in parallel with R2 divided by beta is something you will learn in 115A, or again, if you want to come talk to us about research, there's ways you can calculate like how impedances reflect to different terminals of a transistor. But for now, let's just say this is given. Anyways, the exact stuff here isn't important. What's important is that my IC is directly proportional to beta, which means that even though now I'm only really working as a function of VCC, which is, you know, something I have a fair bit of control over. Sorry, also VBE here, I don't mean literally the voltage between these two, I mean VBE on, like the fixed 0.6 or 0.7 threshold voltage that we had. Right now, it's still dependent on beta. So now I need to get rid of this. And the way to do that is something called emitter degeneration, where you put an emitter or a resistor at your emitter, and now this becomes the same thing, so R2 over R1 plus R2 VCC minus VBE on divided by R1 parallel R2 over beta plus RE, where this is RE. And so now R1 parallel with R2, so generally when you're using a voltage divider for something like biasing, what you'll try and push to do is choose these to be decently large so that you don't burn, like you don't have a huge current flowing through them. But you divide that by beta, and basically this term compared to RE will usually be pretty small. And so what you've effectively done is divided out the temperature nonlinearity of this transistor. And so this setup is what we're going to be using every time we build a common emitter amplifier. Common emitter, by the way, because emitter is common, input here at the base, output here at the collector. And so when you're measuring your input, you're measuring it between the emitter and the base, and your output is measured between your collector and the emitter, hence common emitter, which is the form of amplifier we're going to be primarily using for boosting signals.
Yeah, so just to reiterate, I know it's already said. So here we got an exponential dependence and some input voltage. That's kind of wildly unpredictable. Can't really find, it's hard to get an exact voltage source. Over here we've improved on the bias term, so there's no more exponential dependence on a source voltage, but there's still that strong beta dependence, which does vary with temperature. Then the last step, we added that extra resistor. And what that's done is if that resistor, which it typically is going to be significantly enough larger than R1 parallel R2 over beta, you can kind of ignore that beta term, or its contribution to the overall thing is significantly less. So effectively, IC is going to be stable no matter which day it is.
So to use some typical values just so that it isn't all hand wavy, let's just say R1 and R2 are 10,000 apiece. That means R1 in parallel with R2 is 5,000. A beta of 50 means that that value is 50. Right? A beta of 100 means that that value is 50. RE will usually be something in the ballpark of 500 to 2,000-ish for some of the amplifiers we'll be designing. 50 50 is something you can pretty safely, not ignore in the sense that 550 is fairly bigger than 500, but ignore in the sense that the change from 50 to 49 or 48 because of the temperature dependence of data isn't as significant.
Okay. So
Yep.
yeah.
Those are biasing. So that's your DC bias. Right, so that is emitter degeneration. Now that we're using this though, there is a slight problem. You'll notice that what this does is it makes your gain smaller, because earlier our gain was negative GM RC, and now it's that thing over there, which is alpha is basically beta over beta plus 1. If beta is about 100, you can say alpha is approximately 1. And R pi over beta plus 1, again, ignore the plus 1, R pi over beta is defined as GM. So what you basically, 1 over GM, sorry. So what you have is negative RC over RE plus 1 over GM, and if I multiply this with GM everywhere, you basically have negative GM RC, but now you're dividing it by GM RE plus 1. And so your gain got smaller by this factor. So this is something that we can work around, and we'll get to that next. But this is again one of those trade-offs that we start hitting. You stabilize your DC, you linearize your gain, but what that does mean is you've made it smaller, and now you have to go back to maybe make RC larger to get it back up to an acceptable value. In doing that, maybe you need to make IC smaller so that your voltage isn't as large. What we really want to emphasize here is a lot of these designs, as you add more and more steps and as you solve each problem, you have to go back and make sure none of the previous problems you've solved have become unsolved as a result of this. Alright, so the next slide.
Okay, so our gain is messed up. What do we do about it?
Alright, now we get to AC coupling. And this is, well, pop quiz, hopefully everyone here knows this. What happens to a capacitor at high frequencies?
Its impedance drops.
Perfect. And at low frequencies?
Impedance is infinite.
Infinite, exactly. It's an open circuit. Open circuits in parallel with any resistance is exactly that resistance. Short circuit in parallel with any resistance is just a short circuit. I think immediately it becomes clear why that would be super useful. Because what that means is, if I stick a capacitor in parallel with my RE, then pretty much instantly at DC, when I'm biasing, the capacitor is an open circuit, and so I'm just seeing RE. And then for my AC signal, and I have to choose my capacitor carefully so that it does in fact become negligible at whatever frequency my AC signal is at. So again, impedance of a capacitor is 1 over 2 by FC or something like that. You know what your F is, you can basically find C to make that term roughly 0 at F. And once you do that, it's a short circuit, you're shorting out RE, and so then when you're looking at it in the small signal model, or when you're looking at it the way your AC signal sees it, you see a short at emitter, and your gain jumps back from this to just that.
Okay.
And that's AC coupling.
Yeah. So let's see. Yeah. So remember earlier we said the input for a bias system, it's going to have some DC bias to force the transistor to be in the forward active region, right? Because at a very specific operating point of our choosing. So now the DC component of that will be stabilized because of the emitter degeneration. But for the AC component wiggling on top of that DC offset, that will be unaffected by capacitor, and we'll have our original gain behavior. Okay.
Alright, so now that we've done all of that, let's actually amplify a signal. All we're doing in this slide is putting an input signal into this amplifier we've designed, and then measuring the output through a load resistance RL. Really the only thing interesting here are those two capacitors C in and C out. What those two are doing is making sure that what you're measuring is the AC voltage and not all the DC bias stuff that's also happening around those. You're making sure that the AC input isn't fiddling with your VBE that's been carefully set by R1 and R2. And you're only passing the AC signal into your linearized model of the transistor at small signal. Similar for the voltage, what you're doing is you're kind of filtering out, very in a very rudimentary sense, all of the DC junk, and you're just measuring your amplified AC voltage. Z in and Z out, those are basically the input impedance, which is basically what's the resistance you see if you look in at that node. Tyler, can you point to that node there? There, that on the other side of C in. That's the one. Z in is the basically impedance you would see if you look into the base at that node, and Z out is the impedance you see if you look out of the collector. And again, that's at.
Z out should be RL.
Yeah, that should be RC in parallel with RL.
I see. Yes, yes. I'm
Z out is RC in parallel with RL. But yeah, sorry. But you'll notice that we've used RC in parallel with RL for the gain, but not for typo. But yeah, good catch.
Okay.
So that's the common emitter amplifier, and that's basically the amplifier that we'll use for RAP this year. Depending on what gain you want, you'll probably mess around with the different values, change things, and you'll design a whole bunch of different versions of this. I think the transmitter and receiver we've prototyped over the summer each have about three or four of these in the transmitter, and maybe even more in the receiver, because we had to put a lot to boost the received signal. So about 5 maybe in the receiver. So yeah, we're going to be making a whole bunch of these. It's very exciting.
All right. That's pretty much it for the common emitter amplifier. Are there any lingering questions? How are we doing? Good. Okay. Ready for some math?
Yes. All right. Ready for some math? Let's go. All right.
Getting by bar.
Impedance transformation. Okay. So first things first. One thing you might have noticed is that the transistors that we choose can only, or one thing you should know is that the transistors can only handle so much current. What I mean by that is they're like some micrometer thick layer of silicon, and if you try and force current beyond a point through them, if you try and run 2 amps through them, they will burn up and become an open circuit that's useful for nothing. And so beyond a point, you can't keep increasing GM, which means that the natural way for you to keep increasing your gain is to increase your load resistance, in that your gain now starts being limited by your load resistance and RC. While that's fine for some of the initial examples we'll be doing, where you're designing an amplifier that's a standalone thing, you want to think about what happens in situations where you can't control your load, right? For example, the transmitter antenna is a fixed 50 ohm resistance at 27 megahertz. Other examples might be, you might design a filter that needs to have certain capacitors and inductors at certain values because it filters those frequencies, but what that means is its impedance at that frequency isn't something you can control. And if you have an amplifier if you have the output of an amplifier being fed into a filter, what that means is you don't have a whole bunch of control over what that resistance is. What we then try and do is trick the amplifier itself into thinking that the resistance it's seeing is actually larger than the one that actually is there. This is something that you hopefully shouldn't need to use too much in this project. We're only really mentioning it because it's useful for the final amplification of the transmitter when you're connecting into the antenna, because that's 50 ohm fixed, and 50 ohm is really small compared to standard values of RC. So RC in parallel with RL, you will basically have just RL there. and that can really drive your gain down, because that's just 50 ohms multiplied by whatever your GM is there. And so what we're going to do is something called impedance transformation. Let's start at the start with this. So I have a resistance here on P and some impedance here, XP. My quality factor in parallel for this is XP over RP, I believe. Is it that or the other way around?
I don't know.
Anyone know this? The quality factor for this, is it XP over RP or? I'm pretty sure it's this. And I want to convert it into RS in series with XS, right? And I basically want to choose these values so that it's identical to this when I'm looking in through here, right? So let's start by finding the impedance for that. That's RP in parallel with JXP over RP.
Wait, Vaibhav, it's the other way around. It's RP over XP.
Thanks.
And series is XS.
Series is XS over RS. There we go.
Fine.
Thanks. So I have this is just standard resistances in parallel. If I, let's see, J, RP, XP, RP plus JXP over RP squared minus XP squared, which is J, RP, XP squared over RP squared minus XP squared, and minus, oh sorry, this should be a minus, plus RP XP squared over exactly this thing again. I divide this by XP squared and I basically get Q squared minus 1, and over here when I divide this by XP squared I get Q squared over Q squared minus 1. So far make sense? Okay, so now I know that RS is equal to RP over Q squared minus 1, and XS is equal to Q squared over Q squared minus 1 into XP, which I'm going to say is just approximately XP, and let's just say that's equal to some value X. Yeah.
Okay. Is that supposed to be like RP squared plus XP squared? Or like the, when you like multiply by the common?
Yes, you're right. Thanks. And this is like just this. Okay, so all of that math is functionally only useful for these two equations. I just wanted to make sure you guys knew where these equations were coming from. So I'm going to get rid of this stuff now and go back to the original problem we had, which is I have some resistance here, R, and I need to design something here so that the R2 I see here is greater than R, right? And the way to think of it is, well, RP is equal to RS Q squared plus 1, which means that if I think of this as R with some X in parallel that I am converting to some R with X in series, then this R here is equal to RP Q squared plus 1, right? And then I just need to get rid of this X So I have a JX here, and I have a JX here, and the way to get rid of this JX is to simply put a negative JX here. Did that make sense?
Just a
Yeah.
question. How do you implement the negative JX impedance?
We get to that in just a second. But so far did that make sense? So what it is, I know that this is equal to that. So I take a JX here and make it a series there. And then to get rid of the JX that I don't want, I just add a negative JX. Now, from ECE 110, JX is what circuit component? Inductor. And negative JX is? A capacitor. And so you have your resistance here, that's some fixed value. You have your inductor here L. You have your capacitor here C. And now this thing that you see looking in through here is R Q squared plus 1. So let's say R is 50, right? You want R2 to be 500. So you choose Q squared plus 1 to be 10, and that gives you a Q of 3. Now, you go back to J omega L over R is equal to Q. And in parallel, R over XC is equal to Q. Or I think XC is, it'll basically be this as well if I'm doing that mental math right, but yeah. You know R, you know the frequency you're at, and you know Q based on what resistance you want that to be. And so you solve it to find the values of L and C that you need to build this circuit. And that's impedance transformation.
There you go.
Yeah.
I have a question. So here, that R that you're using is basically the resistance of the antenna, which is 50 ohms.
Sure, yes.
And then you're putting the capacitor and inductor so that if you look into it,
Yes.
it will also look 50 ohms.
No, I'm putting the capacitor and inductor so that at the frequency I'm looking at. So this is something important to know. This only works at this frequency omega. It's pretty narrow band, so it might work for like omega plus minus a few percentage, but if you're looking at it at like omega by 4, it'll work completely differently. You then basically have to resolve a RLC circuit in the frequency domain and see how it responds at that frequency, right? But at the frequency we're at, I want the impedance I'm looking into to be 50 ohms multiplied by Q squared plus 1.
I see.
Let's see. So if you have the output impedance of the amplifier stage going into this thing, you would want to match the impedances. Is that right?
That's match the impedances how? What?
Like to get maximum power transferred into the antenna.
Sure.
Yeah.
Right. So that's one use, for example, which is you try and match the impedance with the impedance of the output of that amplifier, which is when you match impedances you get maximum power transfer. But usually what you will be using this for is, I know RC. From that I can construct an idea for a reasonably large RL, and then once I know what a reasonably large RL is, I look at what my given RL is, find my value for Q, and use that to find my values for L and C. Alright.
So you don't have to. So we showed the math to get up to it. I think we'll write it out later
Yeah.
for your curiosity. But for your purposes, we'll give you the final equation and kind of guide how to use this just be aware this technique exists for this purpose. And in assignments, we'll kind of walk through how it works in more detail. So covered common emitter amplifier, we've covered the impedance transform technique. So last.
You want to take a
Yeah.
time here?
It's almost done. I'm gonna drink
All right.
water.
So we're gonna take a quick break here. Make sure that everyone's cool with common emitter stuff. That was a lot of information. Towards the end, there's some fair bit of math, but key takeaways again are transistors are exponential. When we're DC biasing them, we try and get rid of as many exponentials as we can because the exponentials are sensitive, and the real world is doesn't care about it being sensitive, so we don't want things to stop working every time someone bumps the table. So we try and linearize as much as we can, which is what we do all the emitter degeneration and biasing for. Once we have that, we plug our inputs in, we have a gain, and then we briefly talked about impedance transformation as a way to manipulate our gain if we don't have the option of manipulating the other resistances around it. Sweet. That's fine, team. We'll be back in 5 minutes or whatever.
It's 7:08 right now. So.
Yeah, sweet.
Yeah.
I just gotta like go with it. No, I haven't learned stuff yet.
No, I don't know that either. Like, these are 115A stuff.
Yeah.
So,
Yeah. The only experience I have with circuits in the frequency domain was in 102.
oh, okay.
Yeah. I haven't taken 110 yet.
110 actually is very similar to.
210, I heard.
I mean, it's
just
like
in the frequency domain. Right?
Yeah, it's in the frequency.
Yeah.
Yeah. You just learn how to implement all those things that you learned in 102.
Yeah. Yeah. We'll learn. We'll learn as we go.
So I'm taking 115A, CS33,
Okay.
and 113, which is
Okay.
Diode.
Yeah. Yeah.
The CS33 is really hard.
Review. Oh, you don't like it at all?
I mean, I don't mind it. It's
Okay.
just assembly code.
Okay, yeah, that's the worst part.
Yeah.
I did it in spring.
Oh, you did it?
Yeah.
Okay.
Yeah.
How was it?
I thought it was alright. There's like this one, there's like this one like thing you can do on the Linux machines where you can view all your variables at once, the variable values. I never did, but my friends did it, and ask your TA about it. I forget what it's called though, and that makes your bomb lab very easy.
Oh, I see. Is one of the GDB tools?
Not GDB. No. GDB is so hard to remember and keep track of everything.
Yeah.
Yeah.
Okay.
Yeah.
So that's what you
Yeah.
So basically a command that you just put and then it shows you what values are stored in which variable.
Yeah, it'll give you like a whole list so you
Wow.
can see, and I think it'll update as you go, as you step through.
That's pretty cool.
Yeah, one of my friends was showing me, and it was like, man, I wish I had that when I was doing my bomb lab.
Which one was the hardest lab?
For me, bomb lab.
Bomb lab.
I enjoyed the data lab.
Yeah, data lab was like more of a puzzle.
It's more of a EE thing than anything.
No, that's the thing.
Yeah.
Let's see, the tag lab and I don't remember the last one. The tag lab was fun.
What did you think it was?
Riemann. Yeah, he's great. Yeah. I heard he's even better in person. So, I don't know.
Yeah, I'm thinking it with the Watsky.
Yeah. I heard they're okay. They're good.
It's so.
That's
I don't like his teaching style.
Yeah.
Sure.
What is it like?
It's not that organized. Like, it doesn't give you that many examples.
Okay. Okay. Yeah. Remo's full of examples.
No, that's really
Yeah.
good.
Yeah. I don't know. But you know what? It's just you're completing what your last requirements, right?
Pretty much. No, actually, it's not the last requirements. I still have to take like my core classes, which I'm taking 2 of them right now.
Okay.
CS33 is considered equal.
Mhm.
And I also have to take the electives and take breadth areas, so I'll be here for 2 more years.
Wow.
This year and
Wait,
the next
electives
year.
and which ones?
And technical breadth areas.
Oh, okay.
Yeah.
Yeah, but then there was, I remember specifically.
Yeah.
Do you know which area you want to take this from?
Tech breadth?
On half of the
I'm
department set on an email saying that. if
gonna
you
be
don't
doing
want
both
60 for
CS
today,
and mechanical engineering.
Oh, like a
Like-
combination of both?
I mean, I don't care what I declare as my tech
But I
breadth,
don't
but
know
I'm
if
gonna
that
take
was
those
only for last
classes.
year.
So one of the two.
Last year was like.
Okay, one.
Yeah.
Before after a long.
This year is my speed run year for all my EE requirements.
Yes. Yes.
Yeah. Trying to like get most of those done so I can do like, so I want to do like something like the robotics mechanical engineering courses, because like those seem really interesting, because it's like a all around, you know, engineering project where you like learn from the mechanical design to like when you program it and you do all those things.
Do they offer this course in mechanical departments or?
Yeah, mechanical department. And there's like, I think like a lot of the courses we do in EE satisfy the requirements for that course. Because like mechanical engineers have like a circuits course, EE 10 or 110 satisfies it. 102 satisfies like one of their signals courses. Like that. So, yeah, very nice.
Dude, you can also do the for the capstone projects.
There's a
There's a robotics
Yeah.
project. Are you planning on doing
I was
that?
thinking either that one or the signals one.
This. Oh yeah, that one is also very similar.
Yeah.
Oh, the RF one.
What if I replaced RV with a constant current source?
It's a tool in the toolbox.
Yeah.
that's how I view it. But,
Then, no,
you know
if
what you
you're,
want to do?
I actually don't know. I'm considering between either the RF one or the signals.
Mhm. Yeah.
Because the signals one, I had a friend who did it, and so that was pretty cool.
Yeah.
To learn some
I
stuff
remember
like
we had
camera
to
vision.
like build a.
Like what?
concept.
Like computer vision
Yeah.
and like using a camera and
We did.
yeah, pretty much like the concept is
Oh, it was using a
like at least the project that he did was very similar to EE3. Like you remember?
Okay.
I don't know if you took it with
Like in the
Professor Briggs.
car follow-up.
Yeah, the car, but like it's like advanced.
Yeah. I didn't like EE3 except for that project.
Oh yeah, like the whole EE3 was that project.
Yeah.
The rest of the topics were just
Yeah.
brushing
It
upon.
just like dropped it on you and just
Yeah,
it
it wasn't unnecessary.
Yeah.
That sounds very.
I guess like I feel like that course like helped a lot of people decide if they wanted to be EE. 'Cause I know so many people who switched majors after that course.
Really?
Yeah.
Okay, that's
Yeah.
nice.
So I guess it's good in that respect.
Wow.
Yeah.
What did they switch to?
I think CS or CE.
Alrighty guys, we're gonna bring it home now. There's just a little bit left, and then we'll get you guys out of here. So far we've talked about common emitter, and then talked about this impedance transformation technique. So instead of working up and deriving every little step of what we're gonna call the common collector amplifier, we're just going to present it to you. So,
Oh, wait, before we do that, pop quiz. Based on how we got the name common emitter, any guesses as to why this is called common collector? Shoot, what's up?
You measure your output across the collector. That's why it's called a common collector.
No.
Wait, sorry, no, sorry. The collector is left alone, and then you have your input across the base, and then your output is across the emitter. So that's
Exactly.
why it's the common collector.
Yep.
Sorry,
that's it
I was
right there.
doing the other way.
Yep, that's it right there.
So, alrighty, yeah. So, let's see. So, one thing to note is once the transistors in the forward active, at least at DC, you can kind of approximate that the voltage drop here, VBE. Is that recording?
Yes.
Okay. Yeah, you can pretty much say VBE is going to be about 0.7. So the drop across there is going to be 0.7. So if my input raises raises by 1 millivolt, then the base is going to raise 1 millivolt, and then the emitter is going to also follow that to maintain that constant 0.7 difference between them. So the gain of this thing is going to be roughly, or it's going to be less than or equal to 1, close to 1. So it's given by this expression here. So there's something divided by that same something plus an additional positive term in the denominator, so it has to be less than 1. Now, why do we care about an amplifier that doesn't give us any gain? Like, great, I stick a signal in and I get the same signal, big deal. Very cool. So the key is kind of at this output impedance and input impedance. I can stick in some typical values here, but I'll just convince yourself that this is going to be relatively large and this is going to be quite small. RPi is going to be, let's see.
A quick way to do that is just assume beta is massive. So say beta is 100. If beta is in the numerator and it's 100, going to lead to a large number. Beta is in the denominator and it's 100, it's going to lead to a small number.
Yeah, so if we're feeding this thing with a common emitter, this RS, it's going to be approximately RC, and parallel with a large thing, which is just going to be RC. So this thing's going to, RC, typical value of RC is like 150. RPi is going to be like 2600 with 1 milliamp current. Just take my word for it. So this thing's going to be about RPi divided by beta. You have about 26 in parallel with some large RE. It's going to be pretty small, at least smaller than what you started with coming out of the common emitter, which is about like 150, like I said. So basically what this has done is it has taken the relatively high impedance output of the common emitter, if we're feeding a common emitter into here, and we've reduced the effective output impedance to some smaller value. Now, why is that useful? Well, let's see. Do I want to draw on the board? I might. So I'll kind of disambiguate that diagram. So if we have a battery, let's say we have a 9-volt battery for fun. So if there's a 9-volt batteries have relatively large output or series resistance. You can think of this as, let's just say there's your common emitter thing going into, and it has a large series output resistance, right? So if let's say this is a 1000 or 1000, and then I stick so if I put a really large, if I'm trying to drive a really a load with a really large impedance, let's say 1 milliohms, then it's fine. Then there's a voltage divider here. This is still going to be close enough to 9 volts, so we can say there's still 9 volts being applied. But if this is something small, we're trying to drive an antenna with a 50 ohm load or some other circuit. Trust me, that's 9 ohms. Then now, even though our source is 9 volts here, when there's nothing attached, as soon as you attach this is now looks like a voltage divider. It's going to be as if you had 50 over 1050, about 5 over. It's going to be a much smaller voltage here than you want. So let's probably review, but that's kind of the point of having a buffer amplifier. You reduce, so you stick that in the middle, and you take this, and then isolate it from your, so high Rn, so VA is still going to be approximately equal to Vn. You do your amplification, the common collector, the AV factor is going to be about 1, and then you send that out of a small R out, so that the effective voltage across your load is still going to be about Vn, right? So I think that kind of summarizes the usefulness of having something with a gain of 1. You use it as a buffer to drive a stronger load that would otherwise kind of ruin the output signal from your common emitter amplifier.
Or really anything, like
Yeah.
between just about any two stages in your design, you will often put a common collector amplifier there to isolate the two and make sure that whatever input impedance this one is giving doesn't mess with the actual voltage you want it to be seeing.
Yeah. So there's the
It's really basically just scaling down the input to output.
yeah. So it has a high input impedance, which means you can drive it with something that also has a large
output.
yeah.
from the
So
stage earlier.
yeah, but since it's being dropped across such a large input impedance, it doesn't ruin that the signal doesn't voltage divide it into oblivion. Then it keeps it multiplied by 1, then sends it out over a small output impedance so that it can drive a large load. Okay, so
Other than that, how you would choose R1 and R2 if you were making your common collector amplifier, basic stuff, you bias it so that it's in forward active. We discussed that for the common emitter. Again, you want to choose RE, keeping in mind headroom. Once this is in forward active and biased properly, IC is flowing all the way through here. You know this is ground, you know this is 5 volts. You know that this has to be larger than 0.2. Again, you can't really be dropping more than 4.8 across this. So you would choose RE accordingly based on how large you want that current to be compared to how much you want to eat into this, depending on what exactly you're driving.
yeah. So again, we'll walk through this more later, like in assignment specs, but there it is. I think
And yeah, that's the summary. That's basically what we discussed today. BJT basics, common emitter and common collector amplifiers. We kind of hand-waved through some of the common collector amplifier stuff in part because a lot of the theory there is very similar, and in terms of what we want, in terms of if I want to design this amplifier, if I'm given like a standard circuit diagram, and for the purposes of my design I want to choose the right component values, the process that you need to follow to go through that is very similar to the one for common emitter, in terms of the things you need to keep in mind and the behavior of the transistor that you need to be careful of and work around. So yeah, again, operating principles, gain, input-output impedance for all of those, and then finally impedance transformation. Discuss quality factor, converting impedance, and designing an impedance transformer.
there we go. All right, now the part you've all been waiting for.
Assignment 1.
Yeah, we're going. Yeah, sure. So we have the spec written up. We'll send out an email later today or early-ish tomorrow, just to share that out. We'll put it in the shared drive for you guys, and then you can get started. So we'll get you set up with the software you need. Also, in order to so even though this assignment's all simulation, in order to go into the IEEE lab, do anything in there, UCLA and us, we're requiring that you complete a set of 3 safety trainings. They're pretty typical, any lab you do. will
Any
have
club,
these.
anywhere. And doing them is useful as long as you're a UCLA student, because every club, every lab, anyone will ask you to do it, so just do it and it'll make life easy.
Yeah, so we'll have you do that, just take care of all the administrative stuff. Then we'll jump in, design a common emitter amplifier. We'll show how to do a couple measurements, like, if I want to measure the input or output impedance of an amplifier, where do I stick probes to do that? How do I do that in my software? Optional part, design impedance transformer. I'll walk through that. Common collector, I think we've decided not slam you guys for assignment 1. We'll put that in for it's an important part of designing oscillators, which will be the topic of assignment 2. So we'll kind of save that for that assignment. That said, thank you guys for coming.
That's all for today. Thank you all for coming. Charlie, you want to end the recording? Say again?
When's the assignment due?
That will be in the assignment details. I think